So in this particular problem, we will talk about an orthonormal basis, and we will see how the basis that I'm giving, the set of vectors which I'm giving, will be an orthonormal basis. So I'm going to give you the standard ordered vectors for R3, which is 1, 0, 0, 0, 1, 0 and 0, 0, 1. Okay, so that means there are 3 vectors and the dimension is 3. So this is basically R3 which I'm talking about. The plane is R3, and we have to prove that this particular set of vectors is an orthonormal basis for R3. Okay, so how do we do that? The first thing for orthonormal is we have to check whether these vectors are mutually orthogonal. So the first thing is check orthogonal. And orthogonal means the dot product of two vectors is 0. U dot v is equal to 0, which implies that these are orthogonal. So let's check it for all these vectors. So let's first do it for the first two vectors, that is 1, 0, 0 dot 0, 1, 0. So this is 1 into 0 plus 0 into 1 plus 0 into 0 to 0, which obviously is 0. Let's do it for the next two vectors as well, 0, 1, 0 and 0, 0, 1. So when we do it for these two vectors, again what we see, you will get 0 into 0 plus 0 into 1 plus 0 into 1, which is again going to be 0. And let's similarly check it for the last two vectors as well. Now the first and the last one, that is 1, 0, 0 and 0, 0, 1. And you will see this also getting the dot product is just another 0. Okay, so this one also, let's just write it like that to save some space. Alright, so that means this is an orthogonal set of vectors. So let's call this V. So V is orthogonal. Now next what we have to check, okay, now one more easy thing that we have here. We already know a theorem that any set of vectors, if it is orthogonal, it is automatically linearly independent. Okay, this is a theorem. Orthogonal sets of vectors are always linearly independent. So this is a linearly independent set as well. So V is a linearly independent set, because orthogonality implies linear independence. Okay, now let's check the orthonormality, and for checking orthonormality, the norm of each vector has to be 1. Orthonormal means it is a unit vector. All the vectors are unit vectors. That means the norm is 1. So let's check. Norm is just the length in this case. So let's find the length. We'll use this. Which color should we use? Let's use orange. So let's do this. We'll call these vectors v1, v2, v3. Okay, so let's first find out the norm of v1, which is under root 1 square plus 0 square plus 0 square, which is root 1, which is 1. Similarly, norm of v2 and norm of v3, if you also calculate, it just have 1 0. It just has 1 0 and 2 1 1 and 2 zeros. So again, this will be 0 square plus 1 square plus 0 square, which is again root 1, which is 1. And similarly, this one is also 1. So all the vectors are orthonormal. All of them are unit vectors. So that means V is an orthonormal set. That's also proved. Now what do we have to do is we have to check whether this is a basis. Okay, that means they are orthonormal. This is fine. The first part of this is done. We have to check whether this is a basis for R3. Now recall that whenever we talk about basis, what a basis is a minimum spanning set, and it is a maximum linearly independent set. Okay, so this is what a basis is. Now let's talk about the linear independence. We know this set is linearly independent because it is orthogonal, it is linearly independent. And another way, if you don't remember this theorem, you can just make a determinant out of the rows of these vectors and you can just get the determinant. If the determinant is non-zero, that means the vectors are linearly independent, and you will see that the determinant is going to be 1 in this case. 1 into 1 minus 0 minus 0 into whatever will be 0 plus again 0. So these two are gone. So this is 1 into 1, which is 1. So determinant of, let's call this matrix a V. Determinant of V is not 0. That means this is again linearly independent. Okay, but this thing is shortened by this theorem. If it's orthogonal, you don't have to check the linear independence here. It is implied already. Okay, so this is a maximum linearly independent set. How can I say this is maximum? This is maximum linearly independent because if you have 4 vectors, if you add another vector, say 0, 1, 1, if I add this here, this will become linearly dependent, because you know a simple theorem that if I have Rn as my real plane, Rn, and if I have n plus 1 vectors in that, it is always going to be linearly dependent. If the number of vectors is more than dimension, it is always linearly dependent. So that's why we cannot use this logic here, because our number of vectors is not more than dimensions here, it is equal to dimension. 3 vectors in R3, it is a maximum linearly independent set. Let's talk about the spanning part now. So let's talk about the spanning part. You have to take the 3 vectors and get a linear combination out of them to check the span. A into 1 0 0 plus B into 0 1 0 plus C into 0 0 1. You see, this gives us A B C. For all A B C belongs to R, this gives me A B C, and that just means I can get all vectors in R3 using these 3 vectors. Okay, we can get entire R3 using V1, V2 and V3. We can get all the vectors in R3. This is a spanning set, and this is a minimum spanning set, because if I remove any one vector from here, suppose I remove this vector, I will never be able to get anything other than 0 in the third place. Okay, similar for all the other cases as well. So this is a minimum spanning set as well. Why it is spanning? Because its linear combination of these 3 vectors makes all vectors in R3. And why is it minimum spanning? Because if I remove any of this vector from here, it will cause problem. Okay, so it's a spanning set. That means this is a minimal spanning set. V is a minimum spanning set. So V satisfies all the condition. It is an orthogonal set. It's a maximum linearly independent set. It is a minimum spanning set. It is an orthonormal set, and that means we can conclude. Let's do it here so that everything adjusts in one place. V is an orthonormal. V is an orthonormal basis of R3. And you already know that V is the standard ordered basis of R3, and that means we can conclude as a general conclusion that standard ordered basis of any n-dimensional vectors plane is always going to be an orthonormal basis. Okay, so this was what I wanted to explain about orthonormal basis. Okay, to check any other vector base which is orthonormal or not, just check these relations to be satisfied. So I'll give you a homework question. Check whether this basis for R2 is orthonormal. Okay, check this for R2 whether this is an orthonormal basis or not. So you check for this. Okay, that's all for this video. We'll be back with another topic soon. Thank you.